spending your time with us today. We do want to say that the meeting will be recorded. So Mike, whenever you want to start that, feel free. We ask that everybody keep yourself muted when you're not speaking, but just in general. We're going to handle questions through the chat feature. So in Teams, you can use the chat function, enter your questions as the meeting goes along, and then we'll address them as we get to the end of the presentation. If you have anything else after this, after the meeting, after the webinar, feel free to send an email to phillysei@gmail.com. Sorry, guys. All right, so today we're going to be doing 3.0 University Place. It's a mixed-use facility in University City, Philadelphia. So we'll let our speaker dive more into that, and we will be sending out a PDH, or will be available on our website following this webinar today. Quick look at the board. James Deeney is unable to join us today. I'm James Greco, Vice Chair for this year. The remainder of everyone on here is working hard to keep these things moving in difficult times. Today's speaker is Mr. Blake Worley. He's a Senior Project Manager at Macintosh Engineering, 10 years in the industry, got his bachelor's and master's in structural engineering at Penn State. He's currently registered PE in Delaware. So with a very brief introduction, Blake, if you want to take the screen over, we'll be on to your presentation and we'll do questions and wrap up at the end. And then Blake, make sure you pull yourself off on mute.
Can you hear me now?
There you go. Yep.
Turn my camera off. All right, thank you for that introduction, James. Good afternoon. I'm happy to be here and present the structural design process and challenges for the 3.0 project. I'm an engineer at Macintosh Engineering and want to thank all the engineers at Macintosh who I got a lot of support from and made this presentation possible. So thank you. First, I'll introduce the project. Then I'll share our foundation design process and the framing and lateral systems we considered. And then I'll wrap up with some of the construction challenges. The project is an 8-story, 250,000 square foot mixed use building designed for Class A office space and dedicated labs each floor. The ground floor is a full floor retail space on Market Street. The second floor is flexible for offices, lab spaces, or extended retail. And the upper floor, starting at the third floor, are labs and office spaces for tenants in biotech firms, research institutions, and startups. There's a large green roof amenity space on the low roof that you can see, and the facade is a curtain wall system on the upper floors with brick veneer and more curtain wall along Market Street up to the podium level. The University 3.0 site is on Market Street in Philly between 41st and 42nd Street. It's part of the Platinum Corridor Master Plan. There's an existing University 2.0 building just north of the site, and that was completed around 2013, and more similar projects like this are planned along the corridor. The project location, currently the site's an open lot with street access on 3 sides and existing low-rise buildings on the north side. University 2.0 is about 6 feet from the property line with shallow foundations, and there's a residential building also on the north side that's even closer to our new site, limiting the north side access. We have a great team on the project working for University Place Associates. The architect is Assured Partnership in Philly. The construction team is Dale Corporation McDonald Building Company. And internally, we called the collaborative design approach IPD-ish. It was never formally called integrated project delivery, but we all were part of the design team from the beginning, and the project included some of the key subcontractors from steel and concrete. So came up with IPD-ish. The final design is an 8-story composite steel structure at each floor, including green roof. The floor slabs are concrete on composite metal deck. The lateral system is a braced frame lateral system with an enclosed 2-truck bay loading dock on the ground floor off 41st Street and a full story basement for building services at the foundation level below ground. There's a 3-foot mat foundation at the foundation. And next I'll share how we landed on these designs. Starting with the foundation design, there are these are some of the foundation considerations we can share. Our geotechnical engineer helped us evaluate the site conditions. Their team did, I believe, 12 test borings and revealed bedrock existed on the site close to the proposed basement and foundation levels. So it also revealed that the elevations of this bedrock was varied quite a bit. So we're going to have to plan for that and during construction, because where and what elevation we reach bedrock was going to need to be dealt with then, and we were just trying to prepare for that in our design. The good news is that these site conditions were acceptable for relatively high bearing pressures and allowed for shallow foundation systems to be a viable option. So we looked at spread footings first. Then we adapted that to a spread footing plus an isolated mat design. And then we introduced a spread footing plus isolated mat plus isolated micropile design. And then finally landed on a mat foundation. When we started with the spread footing design, the initial spread footing option was relatively straightforward. There was a high bearing pressure that we could use. The spread footings were at each column and wall footings at the perimeter basement walls. The biggest coordination piece of the spread footing design was just to prepare for meeting bedrock and making sure the construction team was ready for that and come up with a detail where we would undercut the bedrock where that was found, so that that the footings weren't bearing on just bedrock or partial bedrock, and mainly to ensure that the foundations didn't display any unacceptable differential sediments or different detrimental stresses. That when this condition would present itself, we'd excavate farther a foot below, so that we could replace it with compacted fill, and all the footings could be bearing on the same material. This is an early section through the building. You can see the existing University 2.0 building on the right side. Also on the right side, to address the shallow footings of the 2.0 building, we stepped the footings down from there, and we limited the basement footprint so that it didn't go all the way up against the University 2.0 property line. So by pulling that back and stepping the footings down, we could avoid impacting and influencing the adjacent 2.0 footings, and give us a almost full footprint of a basement. So at this time, the spread footing option was looking pretty good until the waterproofing piece of the construction was considered, and the geotech test borings revealed that the water would be above the slab level, the basement floor slab level, and we understood that this water could fluctuate seasonally, and the waterproofing design elevation would need to be higher than that. You can see that line is above everything. So if we waterproofed to that level, it just got complicated really quickly for these spread footings, and just being confident in that waterproofing detailing and construction was watertight. This spread footing option just started to be a little bit more difficult. Can see how many footings and complications or footing complications there are on this plan just by all the line work that the waterproofing detail just started to lead us to other options for the foundation system, and mainly wanting a constant elevation instead of all these steps at footings and walls, and a constant elevation would be desired for the construction of it. So we led to a mat foundation just to simplify the waterproofing details and confidence that it would be watertight. So we designed a 3-foot mat foundation. This mat foundation was lowered about 3 feet below the basement slab, and that allowed for our drains and utility space to also not penetrate the waterproofing layer. And we had a thin basement slab on top of this mat foundation, plus 3-foot interstitial space of utility drains, and then a thin basement slab above that. The material strength we used for foundation was 6 KSI. We varied that to make sure that this was a constant thickness. I believe we started at 5 and played with the material strength and also the concrete column piers. We varied those to control the punching shear in the mat. And that's where we landed on a constant thickness of 3 feet everywhere. And this approach worked well to get a uniform waterproofing level and the mat foundation thickness that we needed below the columns. We also recognized that there were now some areas between the columns where this full thickness wasn't necessary, at least structurally. It was mainly just a construction design choice to simplify the waterproofing construction. So the team, especially our lead team on the project, saw an opportunity to consider a partially voided mat foundation, and in areas where we just didn't need the concrete thickness, that we could maybe introduce a system like this. And it's what you're seeing are just canisters that are voided inside. So it's just adding, just taking up space that would save on concrete weight where it's not needed, and just reduce the concrete that's required. So what we did was we helped coordinate the solid concrete zones that were required, and potentially the voided zones where something like this could possibly be used. The only piece of the mat foundation that was thicker than 3 feet was at our tower crane. The tower crane foundation was thicker, and it was actually 4'6". and that gets that support in the tower, the tower crane above, the freestanding tower crane. Then the mast and mast foundation gets connected and embedded right in the mat foundation here. And that worked well. We just coordinated the utility lines and anything around that space, because it was raised up into the interstitial utility space instead of raising it, lowering it down into, that would just be another waterproofing step that we avoided by moving it up instead of down. In the basement level, there were two lead items that we were involved with: the concrete mix proportions and the water reuse cisterns. The concrete mix specifications was adjusted to allow 40% slag content by weight in instead of all Portland cement. It would replace 40% slag in the foundations, foundation walls, and concrete piers, and that helped reduce the Portland cement and added some lead points. And this 40% was as high as we could go at those concrete elements. But for the elevated concrete slabs, we spoke with our concrete contractor, and they recommended 25% slag content, just so that there isn't a performance and finishing issue at the elevated slabs. So we did it everywhere we could, and didn't affect the performance above. The second item, lead item, was finding a home for two large cast-in-place cisterns that was capturing filtered rainwater, and that's shown in blue. The blue box is taking up a large footprint in the basement, and it's just cast-in-place water tanks. The complication, I guess, was not just finding a home for it, but also providing a lid for it, so that the cistern that we're kind of building inside the building was watertight, but it was also removable, sealable, and walkable over for access to the ground floor framing above it. So we actually found a fiberglass utility cistern lid that is an example of it is shown on the right side, and that actually worked well. And we considered precast lids at first, but I believe just the sequence of when it was going to get constructed and being able to remove the lids easily without too heavy of a crane in the future was a concern. So we landed on this fiberglass lid covering the water tanks. Above the foundation, there were 4 unique floor structures: the loading dock, office floors, labs, and green roofs. At the loading dock was on the ground floor level, and usually these are on grade, but this one was an elevated slab. The basement was below it. To the right of the loading dock, where the truck bearing would be, that is on slab on grade, but right at the dock leveler and inside the building, that's all elevated above the basement. So it also became an opportunity for future access to the basement. And the basement level is meant to be full of building services, and during construction, it's easy to get the pipes or the generators and everything that we wanted to put in the basement down there. But we're also covering it with the ground floor without future access, and without this lid in the loading dock, it would kind of be sealed forever. So this was the design intent was to come up with a removable lid in the loading dock to just for basement access in the future. And it's really only intended to be used once every 10, 15 years to remove it and access it as needed. So it's a semi-permanent removable plank, and the only complication that led to, aside from just this opening and a precast plank to that could be removable, is just achieving a fire rating that would be acceptable. And what we led to was basically sealing this with spray foam each time each time it would be removed. The detail was the plan was just to put the plank back and then seal with spray fireproofing. Otherwise, this joint was a trouble spot for any fireproofing. The office floors above, this is a plan view of the typical floors of the upper floors. The blue space is our intended lab space. Our red outline is the intended office space. The lab space is going on it, while the office space was meant to be exposed. And the architect was interested in several exposed options because of just the sealant intent here. So we offered a couple options of a cellular framing or the castellated framing just in the office space as an architectural element that would also be our floor structure as well. Our largest span on the right side, these did grow to be over 50 feet and just started getting deep on the right side. But that gave us the column-free office space that the architect and team was looking for. The lab design was a little different. Usually the office space, we usually decide the thickness based on a floor-to-floor fire rating, which for this building was 2 hours. And we used a lightweight concrete mix for the office floor structure. But for the lab floor structure, we were starting to have other ideas. We liked the idea of having one concrete mix for the whole floor to allow one concrete pour. But we also recognized that the lab spaces were wanting to be handled a little differently. So we considered normal weight concrete over the lab spaces and lightweight concrete on the office floor areas. The lab spaces were designed for a slightly higher live load than the office spaces, and the owner's team was also aware of some of their prospective tenants could have sensitive equipment and higher expectations of floor sensitivity in the lab area. And so this area, we were looking at increasing the floor stiffness and also increasing the floor dampening. We were just working with the owner's team to find a happy medium for their intent of kind of being flexible to any of these tenants that they were looking at. So the floor slab wanted to have some vibration criteria limits placed in the lab design, and the National Institute of Health and American Institute of Steel Construction has recommendations of some of these various floor slab vibration criteria limits. And there's a wide spectrum of these kind of tolerances from general laboratories to high magnification microscopes, that there's starting to be a lot of variables, and separate variables is what walking speed would we consider that excites the slab, where these floors would be coming from, whether it was slow walking or normal walking or fast walking in a corridor. That there's a number of variables that we wanted the owner's team to be aware of and selecting when we were deciding the tenant space, the lab floor design. So we got a lot of guidance from the owner's lab consultant with what their normal tenants would expect, and also worked with them on just best practices of how to limit their sensitive equipment, essentially making sure our corridor bays are either our corridors are outside of these sensitive bays or at least near column lines in these sensitive bays. So they did some best practices of where to best locate the lab and lab equipment. And then once the team was kind of on the same page, we looked at framing these labs in both directions, looking to increase the floor stiffness as much as we could, as well as dampening the floor structure with increased mass, and therefore we ended up selecting a thicker normal weight slab on the lab space and a thinner, lighter slab on the office space. At our green roof, we have intensive and extensive green roofs above the building at 4 different floor levels. This picture is our heaviest floor level and also our largest green roof space. The largest space is also an intensive green roof with the ability to add a few feet of soil, plants, and small trees. This space therefore became our heaviest design load on the project, ranging from 250 up to 350 pounds per square foot on top of the concrete slab on metal deck. And our office load was, just for comparison, our office load was 100 next to it and could be reducible. So this was almost 2 to 3 times that. And it reflected on our beam sizes on the green roof, and even the metal deck gauge just in this area had to be increased then from maybe standard construction, but that was just to account for the additional green roof design loads. The lateral systems that were considered were diagonal brace frames, concrete shear walls, and a proprietary moment frame system called side plate. Side plate is a field bolted moment connection lateral system. It's designed and detailed by the structural engineers at Side Plate, with steel plates and angles that any steel fabricator can assemble. Some key advantages are that there's no field welding. The system is more stiff and efficient than traditional moment frames, and no diagonal bracing is required, allowing open frames and more planned locations that wouldn't conflict with the architectural program. I'll show that piece next of some of the frames that they selected. The side plate team has a great local staff of engineers that helped with the feasibility study. We shared our RAM lateral models with them early on in the design process, and while we were working on what the best lateral system was for the building. And I know Side Plate is active in a number of our local Philly structural chapters, so I wouldn't be surprised if he's even listening now. He was a huge help. their team did a design assist for the lateral system while we were comparing both of these systems. And their systems could be a little different than where brace frames were located. Our brace frames were located around stair towers, elevators, and another stair tower, trying to bury them in other building service walls. And they were able to kind of spread out their frames a lot farther, which can help their design. One other related design impact for their side plate study is just differences between foundation impacts in brace frames and moment frames like side plate. Brace frame lateral systems tend to add more uplift forces at the foundations than moment frames do. So a full cost comparison really wanted to be the brace frames versus side plate, and also the foundation design for a brace frame versus a foundation design for side plate. So we tried to track all those for the construction team to best vet these lateral options out, and that was a big piece of it. It was the foundation impact as well, as much as just the steel comparison. So this is an example of one of their typical frame elevations, their typical moment frame elevations. You can see it eliminates diagonal braces, and sometimes that can be a benefit of eliminating steel pieces on the project. Their initial design is exactly what we would do by starting with the most economical sizes of beams and columns, and then adjusting from there. So their base design is W30 columns, which are much larger than our W14 columns and W12 columns, but they're perfectly capable of increasing their column sizes at a tonnage premium. But this is an example of their most economical design. Our columns, like I said, we're in the W14 family, so the architect had to be okay with these column size increases, or the team kind of had to get together and meet in the middle. The side plate team also considered using 65 KSI steel, just the isolated columns, mainly at the base of the building. And that was also to reduce column sizes or help with the architectural impact. The design that McIntosh led was the brace frame design, and like I said, we tried to coordinate the locations around the stair and elevator towers. Some of these elevations were intended to be curtain wall and seen from the facade, so we avoided diagonal braces in those locations. I believe there's only one on the west side on 42nd Street, and we also started with all diagonal braces, and then any conflicts with doors, we just adjusted from there. So you can see some of these started to be eccentric braces, and some of them also changed to chevron braces where we couldn't, where there were door conflicts or architectural conflicts. But this is where we landed on. And I think the geometry of this building just led to this system being the most suitable. We had stair towers at each end. That's always a plus, and made for the lateral system to be, I guess, braced this way easier than the side plate design. but we'll definitely consider side plate again. And just for this system, or for this building, I should say, this system was the most efficient. Right now, the design phase is essentially complete, and the project is gearing up to move into construction soon. So we've been working with the construction team, has more subcontractors join the project and into the construction administration phase. And I'll share some of those construction challenges next. A crawler crane was ruled out for this site because there wasn't enough space around the site. So a tower crane was selected pretty quickly to erect this steel. The tower crane is freestanding, so it's opposing no additional loads on the building. It's also shown in the blue highlighted box. But if the building were any taller or a different crane was used, we would need to temporarily connect to the structure during construction and just handle those loads. But thankfully, this is a freestanding tower crane, and the only piece that we had to worry about was coordinating the plan location of it so that it could reach all of our steel picks, but it would also limit the amount of floor openings that we were going to need to infill after we disassemble the tower crane. So the plan location we picked was just off of the tower, the main upper floor tower, inside, but it still penetrates the third floor green roof, the second floor, and the ground floor, headed for the foundation, and that limited to 3 infill details that we'll do afterwards. This is a view of the front of the building facing Market Street. The architectural facade along Market Street is a brick veneer with some long spans for brick support. And the additional complication was not just that there was long span, but the brick veneer wanted to wrap around the bottom of that facade and touch the curtain wall. So it's 2 sides of brick that we wanted to support, but not see the steel to support that brick. So the complication was just the architectural intent to wrap this, and we found that, we introduced a concealed brick support system to the architect, and found several companies that produce standard concealed brick support systems, like could be seen on the left image there, and that's more of like a typical loose lintel connection bearing on the masonry on each end. And we just needed an expanded version of this for the bottom brick support, just because of that width being considered was so wide, and a customized version of this concealed brick support system was needed. And a company called Halfin was able to create that custom veneer support. And this allowed the suspended brick at the typical base to follow the gentle curve that was also occurring on Market Street, and also allow the peerless brick corners on each end of the building that you could see here. We have brick on both those facades, and then brick on both on the underneath side of the of this rendering. So this kind of slick system was able to handle that. Our two tallest columns on the project occur on 41st Street and are unbraced for two tall stories, including the lab spaces above. Our initial design, those are shown in blue there. Our initial design was a square HSS 18 by 18 tube, and our steel fabricator let us know that this large of a shape was not a domestic sized steel shape, and we'd actually have to import it from Japan. So that caused a cost and potentially availability concern, and the steel fabricator has a great engineer on their team who helped select a wide flange column alternative that we could approve. And the only additional effect was coordinating the heavier wide flange column furless, which was already furless from the tower crane location. And it was too heavy to pick as a one column from the ground up to the fourth floor. So we just introduced a splice at the second floor to reduce the weight and allow that crane pick. And thank you. Thank you for listening to our team's work on this project, and I'd be happy to answer any questions you might have.
All right, thank you, Blake. If you keep your screen up in case we need to go to any slides or anything, I'll take it back as we get to the end of the questions part. So we've got 3 questions so far. Remind anyone that if you have a question, enter it into the chat on the right side of your screen. So the first one was about the mat foundation at the base. What was used in the void areas in the mat foundation?
The final design, I guess it's still an option. Right now, the dumb concrete option of without the voids is still in play, and but the system that we're looking at was called Kobiax. It was a Kobiax voided form filler, and there were a couple domestic and international voided concrete products that were possible.
Okay, and that's just a hard concrete shell with void.
No, sorry. Yeah, it's a plastic shell that is just displacing volume. It's just displacing. It's just a canister that's filled with air. There's nothing inside. It's a 2-piece product. So, or some of them are 2 pieces, where it's just filled with air, just to take up space instead of concrete.
Okay, thank you. Second question was for the precast panel in the loading dock. Was there a permanent hoist installed above for lifting that, or the ceiling or the floor slab designed for whatever point load it would take to pick that in the future?
Yeah, we did consider that, and the location made it feasible just to do with a truck crane whenever that separate mini project might be necessary in the future. So instead of buying a permanent crane above it and adding it into the core and shell building, it was kind of passed on to just be part of a separate installation and or partial demo and installing that plank back in the future. So it was considered, but thought of that way instead.
Okay. All right. Can you explain the difference in your lateral system between the side plate system and a typical gusset plate?
The side plate is they're both moment frames. The benefit, I guess, of the side plate is the plates extend out so far that It's actually it increases the rigid end zone for that moment frame. So the moment frame automatically becomes stiffer by their design, and that's their proprietary design that they have their research and research papers confirming their design. So that's like the big advantage of what their moment frame offers, and it's just an alternate lateral system though that can be considered for any building project.
Okay. Do you have a schedule on when you expect construction to be complete?
That's a great question. Right now, I believe we're looking at the beginning of the next year, or to start it, and then probably in the 2-year range for completion.
Okay. The brick wall support at the soffit for the underside, was that part of delegated design, or was that something that you did in the design package?
We helped coordinate it. The concealed brick support, we designed the steel support that this package was connecting to. So our steel was designed to limit brick deflection and was also designed to receive this concealed brick support. That part we designed. The only piece that is delegated was the actual kind of miscellaneous frame, the concealed frame that was coming from the Halfin team. There's rods between structured brick, and those rods thread through it and then connect to their proprietary kind of clamps, and that ultimately just gets bolted to our structural steel. So we helped coordinate it and design for it.
Okay. And then the last question we have listed right now is if there's any special considerations for vibrations or noise from the Market Street subway.
There was, and mainly it was located in the lab space farthest from them, and the retail space and office space is kind of offered as a buffer to the lab spaces beyond it. So that was a piece in just selecting the lab locations. I believe that's why the architect picked the back of the building instead of closer to market.
Okay, great. We got, if anybody else has a question, you got another minute or so. I'll go through the closing slide here, and if something comes to mind, we can ask Blake. If not, we'll close out shortly. So Blake, thank you for your presentation today. I'll grab the screen back for just a minute.
Thank you.
Okay. All right, Blake, that was very interesting. Thank you for a really full detailed building design presentation, top to bottom, with a lot of interesting challenges and solutions. Thank you for that. We do want to show our appreciation with this special pint glass. We'll get that in the mail to you shortly as a small token of our appreciation. We do want to point out our new SEI website, SEI-Philly.com. Is updated with all of our latest information and news and our calendar for upcoming events. So you can see this on there as well for the near future in January and February. A couple defined events, and then some others that we're nailing down later on in the spring. Do want to continue to ask if you want to get your own special edition SEI Philly pint glass. All all you have to do is sign up and give a presentation for 45 minutes, and it's all yours. So if anyone has any projects that you know about or you've been involved in, please feel free to contact us at the email address there or through our website. We'd love to talk with you and have you present. So with that, I don't think I saw any other questions come in. I want to thank everybody for their time and wish you a safe and healthy rest of your day and week and upcoming holidays. Thank you all.